here and I say, well, here's a point whose coordinates are y and h. Here's a point whose coordinates are x and h. No matter where you draw these lines, you get pairs of points. There's only one thing about these pairs of points that are of interest. Every time I get a point y and h going along with a point x and h, these satisfy the heat balance and the material balance. Satisfy the heat balance and the material balance. So I say, gee, I can construct exactly what I want. So I do this. And I'm about to finish the problem. I come over here, y and x. Here is xd, xd. Here is xb, xb. And I start drawing lines by plotting this y versus that x, this y versus that x, this y versus that x. I do that for a few points, and I get a curve of some kind. There it is, a heat and material balance curve. All right? Now, it's no need for me to go through this, but I will tell you what we'll do next. We will move to the bottom of the column below the feed, and we'll do the very same thing. So below the feed, I turn the same crank. I do what I did before. And I find out that the points y, well, I find out that y, which is y and h, and x, which is x and h, and xb, which is xb, and I guess it's hb minus qb over b. Line of straight line. So when that point up there, remember, was a point that we got when we knew it, and in the course of knowing it and knowing where the feed was, so here's the feed, I drew through here and I located a point down here of some interest, right here. This is the point x, this is the point whose coordinates are xb and hb minus qb over b. These guys line a straight line, so I go to this point and I start drawing a bunch of straight lines. And lo and behold, I get points y and h that make material balances with points right here, x and h. All across here for as many as I want. So I draw the material balance curve in the bottom of the column. Maybe it looks like that. So I got all my lines. And I put my equilibrium curve on. There it is. And I'm ready to find out how many stages it takes to do the job. There's the reboiler, there's a stage, there's a stage. It looks like it might be smart to feed right there. There's a stage, and it looks like I got a reboiler, 2 stages in the bottom, a feed stage, 2 stages in the top. And I'm done with the calculation, and I've given up equimole overflow.
Can you say that one more time? What do you have?
I've done exactly what I did with equimole overflow. As you recall, in this picture over here, I would have had 2 lines like this, and I would have said reboiler, 1 stage, feed stage. Took me 1 more stage here than it took me there. This is an approximation. This I've based on equimole overflow. This presumably has accounted for the fact that the flows can vary through the column. So we've pretty much got that under control. That's how that calculation goes, and it's hardly any different than before. It's just that rather than use the material balance by itself and assume something about the flows, I should use the material balance and the heat balance and let the flows take care of themselves. So I get a slightly different looking thing, and that's how the calculation goes. Now, here's the thing. So we have made an equimole overflow calculation. And we've made a calculation taking into account. So first, all we had was lambda 1 and lambda 2. What did we do? We assumed that lambda 1 was approximately lambda 2, and we assumed L and V were constants. And we went and made the construction that looks like this, and we got an answer that looks like that. Second thing we did, we just did it. The second thing we did was we said, okay, we got a shitload of data, lots of data. And so with lots of data, we began trying to allow the flows to change by making the heat balance. The heat balance is going to require how the flows change. And got a diagram like this, made our usual calculation, and lo and behold, we have a number of stages to do the job here, a number of stages to do the job here. Now, there's one sort of a funny point. I think the following is true. I think a person ought to always make that approximation first to find out what the lay of the land is. However, there's a small snag you got to worry about. I can make this approximation first, and I can calculate a minimum reflux ratio, which tells me that I can't do the job at a reflux ratio below that value, no matter how many stages I have. The minimum reflux ratio here and here won't be the same. So, when you come over here and calculate a minimum reflux ratio, this minimum reflux ratio could be higher than that one. So over here, you say, I got a minimum reflux ratio. I can go all the way down to there. Well, maybe not. Maybe the biggest thing that's important about this construction is that the minimum reflux ratio is going to change. So, those are two things we can do. Now there's an intermediate thing we can do. Let's just sketch what it is. Third. Okay, I don't have full data, but I have a lambda 1 and a lambda 2, and I observe they're not nearly equal. That's all I know. All I know. So what am I going to do? Well, I'm going to work very, very hard to save that construction over there. And all I've got to do to change that, save that construction over there, given that this is all the data I've got, is I will simply adjust the molecular weights of these things to how I want them. So that's the move. So I am going to say, look, I've got these latent heats, lambda 1 and lambda 2. Lambda 1 and lambda 2, these are latent heats per mole. I will divide them by their molecular weights. These are now latent heats per pound. Latent heats per unit mass. Now, these were not equal or not close. It may be when I get to here, I find out that these latent heats per unit mass are the same, or very nearly the same. At that point, you would say, you should work this problem in mass units and assume the flows are constant through the column in mass units. That would be a reasonable thing to do. But suppose you find out that these numbers aren't close either, these weren't close, these aren't close. There's another move you can make. You can say, I'm going to fiddle with the molecular weights. Now look, I don't know what you think of molecular weights, but to us, molecular weights are just ways of grouping mass. I just come in and say 12 grams of carbon is a new unit of mass of carbon. So I'm going to say, why do I have to group things that way? I will introduce molecular weights M star and M2 star, and I will choose them so M1 star lambda 1 over M1 equals M2 star lambda 2 over M2. Now, these are the molecular weights. What should we call them? They're not per mole. Let's call them per star mole. So we're saying that the latent heats per star mole for 1 and 2 are the same. So we're going to assume constant star mole overflow. That's our plan. So what we have to do is, given a problem in normal mole units, we have to convert it into star mole units, and then so if I ever get this thing in star mole units, I am going to assume that when I plot this thing, everything's in star moles now. I'm going to assume I got a straight line in star moles, a straight line in star moles. I'm going to step it off, and that'll undoubtedly be a better approximation than equimole. Probably won't be as good as if you had full data, but boy, this is a nice back of the envelope calculation that doesn't require you to do all that jazz. So how does this go? So X1L can be moles per time of component 1. X1L divided by M1 is going to be pounds per time of component 1. M1 star X1L over M1 is going to be star moles per time of component 1. Total star moles flowing then is the sum of this for component 1 and component 2. So L star is got to be M1 star X1 over M1 plus M2 star X2 over M2 times L. That means anytime I have a flow in this thing, and I know its composition, I can get the starred flow. It's also got to be true that if I go M1 star, X1 star, L star, I better get M1, X1L. So it looks like X1 star is got to be M1 X1 over M1 star divided by that group. M1 X1 over M1 star plus M2 X2 over X2 star. Everywhere I know a composition in moles, I know the corresponding composition in star moles. So I now have all my flows, all my compositions in my new units. So I take my problem stated in moles, convert everything into these new moles, do what I've done before, making the assumption that L star and V star are constant in the top, L star prime and V star prime are constant in the bottom. I get straight lines, I step it off, I have the number of stages, and I'm done. Okay, so we can do all that stuff, right? Okay, so let's give this up and turn our attention to something a little more interesting. Here is a picture that the people that are doing design nowadays have probably come to know and love. But this is a C equal to 2 version. So here I have some data. C equal to 2. And at the assigned pressure, given P, I'm going to plot Y versus, no, I'm not either. I'm going to plot, what shall I plot? I'm going to plot T versus X or Y. And, yeah. So let's suppose the vapor pressures tell us something like that. I can have two sorts of pictures. Here's a picture. This system has what is called a least boiling azeotrope. It could have turned out like this. This system has what is called a greatest boiling azeotrope. We're going to suppose that, well, let's take and look what Y versus X looks like in the two cases. So Y versus X in the left-hand case looks like this. And Y versus X in the right-hand case looks like this. And of course, these are, I guess that's all right. This is the azeotrope composition in the one case. That's the azeotrope composition in the other case. Now, I guess there's a number of questions about these azeotropes that might be worth discussing. Here's something for you to go home and think about. Let's suppose the following. You know your system's got an azeotrope. So here's something that's worth trying to get straight. You know your system's got an azeotrope and you're going to boil it. So you decide to boil your azeotrope at the pressure P. So here you are trying to boil. You put it in here, you begin driving off vapor. You turn the fire on here, and you're driving off vapor. Kind of looks like a Rayleigh still, but I'm not really interested in that aspect of it right now. Let us suppose we load into here the left-hand azeotrope at time 0. Now, it turns out that the left-hand azeotrope is at 1/4 pi. Remarkably enough, and of course the first thing you would say was, how the hell could you ever find out it's 1/4 pi? Well, let's don't worry about that. I'm going to load 1/4 pi in there, and I'm going to begin boiling. Well, here's the problem. I can't exactly load 1/4